I'm too fat for my data, too fat for my distribution. That's 4 syllables long. There's no way any song is ever going to get that word in. We have here prices for a whole bunch of tutors for hire. We actually do maintain a list of tutors for hire, and right now at the beginning of the semester you don't think you will ever need them, but it might be nice for you to know that there are people you can hire. These prices are made up, but that may not be unreasonable. It kind of depends on how busy they are and how much they're in demand. That list can be found on my main website. There's also links you probably got and didn't pay attention to. So we want to talk about the spread of data. How spread out are these numbers? How fat is that distribution? There's 4 main ways we're going to talk about it. We're going to talk about range, IQR, standard deviation, and variance. And range is the one we'll talk about least in this class, although you have to learn the definition here, whereas standard deviation we'll use the most. What is range? It's the maximum minus the minimum. All the way up from the top to the bottom, that's 164. So we could say the prices of tutors have a range of 164 from the lowest to the highest. That's not all that useful for several reasons in real data sets. Sometimes you can get an outlier that would totally mess up your range. So learn the definition now, then you won't ever really see it again, the poor thing. Now IQR is really easy if you're comfortable with how to make a box plot. You have your median, minimum, maximum, your Q1, and your Q3. IQR is defined as the distance between Q3 to Q1. So take Q3 minus Q1. Now do keep in mind, if you trust your calculator to just give you the answers, there's more than one way to do a box plot. We are doing way simplified rules. You can actually see clearly, obviously, the problem here. Minimum to Q1 isn't actually the same distance as Q1 to median. So very simplified rules here, but our Q1 is here at 22. Our Q3 is here at 166. IQR says, how big is the box? Ignoring the whiskers on the end, just how big from 166 to 22. And in our case, that would be 144 as the distance of the box. In other words, the middle half of the data ranges between 144 units. Now, the equation for standard deviation looks very intimidating the first time you see it. But I'm going to walk you through it slowly. It's doable. Here's what the equation is trying to say. The xi are the data points. Let's take each of the xi's and subtract it from the average. How far is it away from the average? And then we're going to square that. This sigma you've seen before for the mean, that means add them all up. So we're going to add up those squared differences and divide by n minus 1. This n minus 1 has a name. His name is degrees of freedom. We won't need to worry about that for a long time, but in a couple of weeks that actually will matter. And then in the end, you do a square root of that answer. So let's walk through this slowly. I'm going to start with each of my xi's. I've got 7 of them. And I'm going to take each of them minus the average. I've calculated the average is 72. Then I'm going to square those numbers. I'll add them all up, divide by n minus 1, and take the square root. So each of these numbers minus 72 gives me these numbers. Notice some are negative because they are below the mean. Some are positive because they're above the mean. If you added all those up, you'd actually get 0 because the mean was right in the middle. They have a name. Their name is deviations. We will use that term in a couple of weeks, but for now, that doesn't necessarily matter. Let's square each of these. Notice that they have gone positive. If you do this step and you end up with negatives, you've done something wrong. These have a name. They're called squared deviations because we're not really that creative when we come up with names. Our next step, let's take each of these squared deviations and we're going to add it up. And now we're going to divide by the degrees of freedom. Why degrees of freedom? In a nutshell, if I told you the average, could you calculate which number was what? And the answer is, if you told me n minus 1 of them, if you told me all the numbers except the last one, and then you told me the average was 72, I could figure out the last one. So in a sense, that last one isn't random based on the mean. So here we divide by the n minus 1 that are still random. In our case, it'd be 7 minus 1. We're going to take this, divide it by 6. That's 5184. And if we took the square root of that, let me do it in my head, it'd be 72. So our standard deviation is 72. The words you could use would be like, from the mean, which was also 72. Really? Really? Okay, so I happen to pick an example where the mean and the standard deviation match. That is not going to happen. Please do not think that that is something you can expect to have happen. In fact, now I'm probably going to have to do another video about this just to make up for that. Okay? In our case, from 72, if we go out a standard deviation, which was also happened to be 72, that'd be like 140 down to close to 0. Would that capture a good chunk of our data? Yeah, that'd capture all this data. If we went out a second standard deviation, it should capture almost everything, which would take us from 140 up to 210. Yeah, sure enough, okay? And when we talk about the normal distribution, standard deviation is going to become even more important. Now, let's move on and talk about variance. Variance is the standard deviation squared. You ready for this? Here's how we do it. We take 72 and we square it. Actually, that number's already on the board, right? Because this is what we had before. Our variance is 5184. Can you picture that or use that in any sort of a sentence? Probably not. It's really tough. But this shows up in equations all the time. In other words, the standard deviation ends up getting squared lots and lots in the math we're going to do. So we just finally gave it a name, the variance, 5184. This is the one that you can actually try to picture capturing data. Can't believe the mean and standard deviation were the same on that.